Ram, please go ahead and start your presentation. You're live.
Okay, so do I put from my screen or I already uploaded there?
They'll be navigating for you, so you can just go ahead and tell them when to move the slides.
Okay, so I'm not seeing my slides yet.
They are up on the screen. So you're right now you're on your title slide, design of next generation battery packs for a sustainable future.
But I don't see. I don't know. Is there something else I need to?
Do you see your own camera, Ram?
Do you see me?
Yep, we see you.
But I cannot see my slides.
Do you see yourself?
No.
Okay, you may need to go back to the tab that you had open with the StreamYard link.
Okay, I see myself. Yes.
There you go. And now do you see your slides as well?
Okay, okay.
There you go. Thank you so much.
Thank you. So our project is focused on the development of next generation materials for sustainable battery technologies. So the energy use is now dominated by fossil fuel that is finite, and more importantly, the use of fossil fuels lead to air pollution and health hazards, and there is a lot of interest to use renewable energy sources, particularly solar and wind, but they are intermittent. So right now, storage of the electricity produced from solar and wind is the bottleneck to use renewable energy sources. So for storage, battery technologies are the most viable near-term option. And in terms of batteries, lithium-ion batteries are the most versatile. But right now we use in lithium-ion batteries expensive materials. So here, particularly, I want to take graphite that is used as the anode. And graphite has few problems. One, it has low capacity, particularly it occupies more volume or more space, so it leads to lower volumetric energy density. Second, the operating voltage of graphite is close to that of lithium metal. Therefore, when we do fast charge, lithium can deposit in the form of dendrite, and that leads to safety issues. Third, it involves expensive processing, high temperature. So I can say it's hard to make, so it's expensive, and mostly good graphites are actually imported. So that's not good. So that means we need to focus on developing materials that are sustainable, particularly domestically produced and domestically manufactured here. So our approach is, instead of graphite, use alloy anodes, but there is a lot of research being done or has been done with alloy anodes. Generally, for example, silicon or tin disperse in carbon matrix, and that leads to a couple of problems. First, it occupies more volume, so that leads to low tap density. Tap density is a term used in the battery community. That means when you pack, you are not packing it well. It is occupying more volume. If it is occupying more volume, then it will lead to low volumetric energy density. And it also leads to high processing cost. Why I talk about volumetric energy density? For all portable applications like laptop or cell phone or electric vehicles, volumetric energy density is the most important because there is not much space to keep the battery. So our approach is not to use that kind of dispersing the active material in a carbon matrix, and then you have to make slurry, coat the slurry, dry it, all those steps which involves graphite and the other ways of using alloy anode can be eliminated with our new approach. So what is that new approach? using metal foil alloy anodes. And this can potentially increase the energy density by more than 50%, reduce the cost by greater than 20%, and more importantly, they can also give potentially fast charge, 10-minute charge. We all want to charge our batteries pretty fast, but right now we cannot. And they can also be cheaply produced at kilogram scale. So these will also eliminate, like I said, some of the steps involved in the graphite anode. The volumetric energy density with our new approach, as you see here, much higher than the volumetric energy density we can get with other processes or other type of alloy anodes. So to do this, we have brought 5 investigators with different backgrounds to work on this. My group, and Professor Huang from chemical engineering, and Venkat Subramanian from mechanical engineering. They do atomistic and BMS modeling and techno-economic analysis. Again, Professor Hales and Manthiram along with Venkat, and life cycle analysis of the foil anodes by Professor Hales and my group. So the experimental design is very easy. Making these materials is very easy, and we also have a lot of flexibility for compositional, structural, and geometry tuning with this approach. For example, if you add 1% of silicon to aluminum, you can see a big difference in the performance. It also allows for fast screening of various materials, because you just make the metal foil anode, just a foil, and then test them, rather than going through making slurry, casting, and then electrode drying. All those very tedious steps can be avoided. So with this approach, we have tested actually several materials, metals, as you see here, aluminum, indium, tin, lead, and other things. In that, we found 8 elements have sufficient capacity to be used in this process. And in that, we select just 4, particularly aluminum and tin, and indium and lead can also work, but lead is toxic, and indium and tin are more heavier than aluminum, for example. So the process is very simple. It will have an inactive matrix, like for example, aluminum. In that you disperse tin, that's one approach. Or you can have aluminum itself is an active material without anything else. So here you make an incard of the alloy, then you cold roll it, and then after cold rolling, you can cut and fold or stack and cold roll. If you do it repeatedly many times, you can have a nice dispersion of the active material and the inactive material. This is the beauty with this technique. Very easy to do, just cutting, rolling, That's all we do. If you don't do that, then you will have this kind of segregation, which is going to create a lot of volume changes and performance degradation. So one example I show here, aluminum versus 1% silicon doping. If you see that, you see a much big improvement in the capacity. One issue is whenever you have a solid metal foil, one will always be worried, how am I going to have lithium diffusion into the material? As you see here with this one of these materials, this is the starting point. As you keep on cycling, they create their own pores. So through that, the electrolyte can move through, as well as lithium ions can move through. So that's the beauty with this method of making foil anodes. So we cannot bring a new way of making stuff or new battery chemistries and create more pollution than what we normally get with fossil fuel use. So we take this as a holistic approach. We take into consideration total energy use, emissions involved, toxicity involved, habitat destruction, social impact. So we have taken all of this into account. So you can see here, if you use graphite, this is what you see in terms of global warming. If you use just aluminum, it's less, but it is still significant. But if you take used aluminum, for example, used aluminum can, then it is much reduced. So there is a big advantage in terms of cycle life and less pollution. Venkat?
Good afternoon. Can you all hear me? So we created an Excel toolbox for performing the techno-economic analysis for this next generation battery material. This was created with the help from backpack from Argon and then modified for this specific material, zinc tin alloy. And this involved the cost for the materials, the facility, the labor, and then combining that with some forecasting on what would be the cost in the future. And this Excel spreadsheet is easy to use, and anybody who is interested can get an access for this. And it will be shared without any restriction for anyone. Next slide, Ram. Thank you. And we also tried to model this next generation battery material by looking at the microstructure evolution inside this battery, in this anode material. We see that when you charge and discharge this battery material, there is hysteresis. And in addition to that, the morphological change makes a difference in terms of the performance of the battery. So we developed an electrochemical continuum model for this device, and that is able to predict this charge discharge curve with reasonable accuracy. And the next step would be to take this to battery management systems to identify the charging protocol for this chemistry. Thank you.
Yeah.
Yang, if mic is not working, you might have to refresh the browser. Kayla, can you see if Gyong is here? I saw him in the main studio. Maybe he's not in this special studio.
Yeah. Oh, now.
Yeah, he's starting.
Okay. Great.
Go ahead.
Yeah. So as Ram mentioned, the performance of anode materials tends to be improved by adding a small amount of dopant. So using first principle atomistic simulation, we have examined the doping effect on the lithium behavior of tin and aluminum-based anode materials. The top figures shows the structural evolution of antimony-doped tin with the lithium at the atomic scale. Here, the dark yellow ball indicates antimony. The gray and the purple ball represent the lithium and the tin atoms, respectively. I'm not going into the details of the results. The key findings from analysis of these results are that the lithium atoms preferentially interact with the antimony over tin, especially at the early stages of lithiations. And the antimony atoms remains well, the previous slide, well dispersed in the lithiation and the delithiation process if the antimony concentration is sufficiently low. The weak aggregation and the preferential lithiation tendency of antimony dopant in the antimony doped anode, tin anode can contribute to enhancing its structural stability during cycling in comparison with pure tin and the tin antimony alloy cases. As summarized in the next slide, we have also compared lithiation-induced changes in the electrochemical, transport, and the mechanical properties between the antimony doped and the pure tin system. So our study highlights the importance of a low concentration and the uniform distribution of antimony in order to obtain desired properties of antimony doped tin as an anode for lithium-ion batteries. So we have also examined the other dopant in the next slide, such as the arsenic and the bismuth. As you can see here, arsenic, antimony, and the bismuth, they are in the same family, but they have different electronegativities. So as briefly shown here, the lithiation behavior of tin varies with choice of dopant. So our work suggests that the performance of tin-based anode can be enhanced by via fine-tuning of doping. Okay, the next slide. In the previous slide, Ram presented that the performance of aluminum foil anode can be improved by adding a small amount of silicon. So we also try to understand how that happens. So when a small amount of silicon is incorporated into this aluminum matrix, we have found that the aluminum structure becomes highly disordered, as shown in the top left figure, but not necessarily all impurities induce the structural disordering. For instance, the copper does not. Then we look at the radiation behavior of silicon-doped aluminum. In the top right figure, the blue and the gray and the green balls represent silicon, aluminum, and the lithium atoms, respectively. The results clearly show that the preferential interaction of lithium with the silicon of aluminum. So in addition, the lithium diffusivity tends to be enhanced when the aluminum matrix is doped with silicon, as presented in the bottom middle table. The next slide shows the synergistic effect of dopant and the structural disorder on the radiation performance of the aluminum-based anode. As shown in the right figures, in the crystalline structure, the aluminum is not hardly lithiated. But we have found that the lithiation performance is significantly enhanced when the aluminum structure is highly disordered, and also silicon dopant are present in the aluminum matrix. So our results clearly support the experimental observation of improved performance of aluminum foil anode with a small amount of silicon incorporated, like what Ram presented. Okay, this is it for my presentations.
So overall, replacing the graphite anode in the current lithium-ion cells with low-cost alloy anodes and low-cost manufacturing technologies can make the lithium-ion-based technology more sustainable. As we move forward, cost, affordability, sustainability will be the single dominant factor, because the field is exploding, and that the number of batteries we have to make is going to be enormously very high numbers. So the new approach we have developed involves a very simple process of making the foil and then just cold rolling, ingot and then just cold rolling. So we have brought together a team of experimentalists and modeling people together, and that has helped us to have a unified approach in understanding what is happening with this new approach. So this is the publications coming out of this project, and several of them have been already published, at least 6 of them, and another 5 of them are in preparation currently. Thank you very much.